Okay, good afternoon. We have started our discussion on computational methods for multi-phase flow in the previous class. Before going to the discussion on multi-phase flow, let us try to revisit some concept of the computational fluid dynamics. Some of you, those who have not taken the course on computational fluid dynamics, may find difficulty in understanding the further lecture. So what I will do in this lecture, I will briefly try to summarize some concept of computational fluid dynamics, so that whenever we will be discussing the uh, computational methods for multi-phase flow problems, then it becomes easier for you to understand these concepts. So typically, as I told you, that for fluid flow problems, we will be mainly referring to the finite volume method. However, understanding of CFD becomes quite simple with the finite difference method, and if we have the basic idea about difference method, then quickly we can transform the relations to finite volume method, and ultimately whenever we will be talking about the multi-phase flow problems, there also we will be referring to the finite volume method only in this particular course. So in terms of finite difference method, some of its key features are: the first point is it typically deals with the structured mesh. Okay, so if we have unstructured mesh, then we will not be able to use the finite difference method. And second important point is, again, whenever we use the structured mesh, we have to consider our mesh elements orthogonal. Okay, so for example, if this is my domain, if this domain I have to divide in such a fashion so that a proper structure is maintained. Okay, and along with the structure, one additional thing which I have to maintain is that the angle between these two sides should be 90 degree. So grid should be orthogonal. Okay, and whatever the point of intersection of these parallel lines is, that point of the perpendicular lines is, this point of intersection is considered to be my node points or nodal values. Okay, so these are the locations where data is typically stored, and these locations are used for transformation of partial differential equations into algebraic equations. Okay, another key feature of this method is that it cannot be used for unstructured elements. Say you have this type of complex situation where grids are not orthogonal, and also the structure is actually very complicated. So this type of unstructured arrangement cannot be used. So typically you will be finding that if you have some curved domain, okay, say something like this, then it is easy. Say if you have geometry something like this, then it is easy to divide this curved domain into a large number of finite volumes. However, you will not be able to get a proper structure at the outer boundary. So whenever you have to solve the curved geometries using finite difference method, then comes the issues. So either one of the ways, if you have some curved geometry, then you just keep on maintaining the structured arrangement, and after maintaining the structured arrangement, if this is the your portion within the domain, then this outer portion is actually in all these outer cells. First values are extrapolated, and these extrapolated values are then utilized to interpolate the values at all these curved boundaries. So these outside nodes are typically called as ghost nodes. Okay, another way of dealing the curved boundaries using the finite difference method is that these curved boundaries, if we have yes, any question or okay, so if we have any regular arrangement of curve, then that regular arrangement of curve, by using grid transformations by using grid transformations, it can be converted from one plane, say xy plane, to some another plane, zeta, eta plane, where the unstructured arrangement in the xy plane can be converted into structured arrangement on zeta eta plane. Okay, so for that we have to use some mathematical transformations, and under these scenarios we can use the finite difference method. This is the brief overview about the finite difference method. Now if we have to implement this method, ultimately what we need to do, all the derivative terms we need to write in terms of algebraic difference equations. So how it is done, I will give you example with the help of one dimensional grid arrangement. Okay, so what do you mean by one dimensional grid arrangement? So the arrangement which I have shown over here in this previous system, here you can see one grid structure is along the x-axis, other is along the y-axis. Okay, and this is a two-dimensional plane. So on this two-dimensional plane, if I have to define any node, then I will be using two indices I comma j to define this node location. Now I will be my index in x direction and j will be index in the y direction. So in this way, if arbitrarily this is my location I comma j, then I can define the next location as I plus 1 comma j. Next will be I plus 2 comma j. Likewise, if I keep the I fixed and move in y direction, then it will be j plus 1 and this will be j minus 1. So I comma j minus 1, I comma j plus 1. Okay, so this is a two-dimensional grid arrangement. In the scenarios where my phenomena is mostly taking place in a single direction. For example, if you consider that you have a pipe and in this pipe inviscid fluid is flowing. Okay, so what will happen? We can take at any location. This is arbitrary choice. Okay. So this is my pipe, and in this pipe, if when I consider that a viscous fluid flows, what happens? I am having generation of velocity profile something like this. Okay, where if this is the axial location z and this is radial location r, in both the directions r and z velocity is actually varying. So velocity is a function of both r and z. Okay, now if I say that I only have the flow of inviscid fluid inside a pipe, okay, in that scenario what will be happening? My velocity profile will be straight. Okay, and in this way it can happen that velocity from this point 1 to point 2 in z direction is actually changing because of any type of phenomenon. Okay, so then velocity will be a sole function of z. Okay, so in this type of one-dimensional flow approximations, even this type of situation you may encounter in if you consider purely one-dimensional heat conduction inside a rod. Okay, what will happen in this scenario if you consider 1D heat conduction? So you will be assuming that temperature at all the locations is same, say T1, T2 or T3, and temperature is only the function of direction z. Okay, so in these scenarios, whenever I will be defining my elements, I can define actually the line element where variation is only taking place along the which direction? Z direction. And in the r direction, I need not to define any node point because in all the radial locations value is actually uniform. Is this one clear? So this type of approximation is called as one-dimensional flow approximation. And in the 1D approximation, if I consider that my one-dimensional grid is something like this. So arbitrarily, if this is my point I, this will be point I plus 1 and this will be point I minus 1. Is this one clear? Now, you have to understand that what is our interest over here. Our interest is to solve fluid flow and heat transfer problems with the help of numerical methods, whether finite difference or finite volume. Okay, so ultimately our interest will be to transform the governing equations of fluid flow and heat transfer into the algebraic equations. Okay, so typically the governing equations of fluid flow and heat transfer are partial differential equations, and if I simply talk about the Newtonian fluid, then equations are typically known as Navier-Stokes equations. Okay, and if you see the mathematical nature of the Navier-Stokes equations, these equations are of second order and these are non-linear equations. Okay, so equations for solving fluid flow and heat transfer problems are nothing but second order non-linear differential equations. Is this one clear? So it means that the meaning of second order is that if there some derivative term is existing del u by del x, there this is the first order derivative term, there can be some term del square u by del x square, which will be a second order derivative term. Okay, and even some of the terms you will be finding del square u by del x del y, which involve the mixed derivative of second order. Okay, so ultimately if you have to convert the governing equations into algebraic equations, then you need to estimate the values of first derivative, second derivative and mixed derivative. If you are able to define all these derivatives in terms of algebraic equations, then ultimately your entire equation can be defined in terms of algebraic equation. Is this one clear? Now, whenever I will be considering the one-dimensional grid structure where variation is taking place only along a single direction, then using the Taylor series approximation, if I have to calculate the value of any parameter u at point I plus 1, by considering that I am calculating this value with reference to point number I, and in between I and I plus 1 if the distance is delta x. Okay, then what I can do, I can simply apply the Taylor series approximation over here, and using the Taylor series approximation I can write that u at point I plus 1 will be equal to u at point I plus delta x into del u by del x at point I plus delta x square by 2 factorial into del square u by del x square at point I plus so on up to like this. Okay, now from here if I calculate the value of del u by del x at I, then del u by del x at point I is given in terms of u at point I plus 1 minus u at I divided by delta x. Okay, and plus what I will be having, sorry, minus I will be having delta x square, and this delta x square is divided by delta x. Okay, so it means delta x by 2 factorial into del square u by del x square plus delta x square by 3 factorial into del cube u by del x square at I plus so on up to like this. Okay, now whenever I am considering this numerical approach, always we try to maintain delta x to be a smaller value. Okay, what is the reason? You will be understanding that if delta x is small, then among all these terms, which value will be smaller? Which value will be dominating in magnitude? First term will be of dominant magnitude. Okay, so if this term is dominating and I am neglecting all the terms, then I can say that my del u by del x at point I is equal to ui plus 1 minus ui by delta x plus order of delta x. Okay, so this type of numerical approximation, why I am calling it as approximation, because ultimately if you have to calculate del u by del x in exact way, then in your Taylor series approximation you have to consider the terms up to infinity. But over here what we are doing, We are only considering the first term, and all the remaining higher order terms of this Taylor series approximation we are actually neglecting. So that's why del u by del x at any location I can be written in terms of u at I plus 1 minus ui by delta x. However, this is an approximate value. Okay. Now, if you see the left hand side, what is left hand side? It's a derivative term. What is right hand side? It's algebraic term. So it means if you replace in any derivative equation, any partial differential equation, first order term with this type of approximation, then you will be getting algebraic equation. Now, one important point you have to understand that whenever we are calculating this particular value, derivative at point I, what we are doing? We are using the value of u at point I plus 1 minus u at I. So it means on the present node and one node in which direction? Forward direction. So that's why this type of approximation is called as forward difference approximation. Okay, so this is called as forward difference approximation. In the similar way, if you have to calculate u at point I minus 1, that will be becoming u at point I plus, now what will be difference between I and I minus 1? Minus delta x into del u by del x at point I plus minus delta x whole square divided by 2 factorial into del square u by del x square I plus so on up to like this. And from here you will be getting that del u by del x at point I is equal to u at point I minus 1 divided by delta x. So this type of approximation is called as backward difference approximation. Okay. Now if you do the other arrangement, whatever this forward equation I have written and backward equation I have written, if you take the sum of these two, or even if you subtract these two, so if you do 1 minus equation number 2, you will be getting del u by del x at point I equal to u at point I plus 1 minus u at point 2 delta x and plus whatever the highest order term I will be getting now, del x square by 3 factorial into del cube u by del x cube at I. Okay. So what is the order of accuracy over here? Hello. Hello. एक वेबसाइट पे आप आइए और स्टूडेंट आपको कॉल करेगा. ठीक. Okay, so this is del u by del x by I and this entire quantity plus order of delta x square. What we call this scheme? This scheme is called as, please tell me, central difference scheme. Okay, so this scheme is called as central difference scheme. So in the central difference scheme, when I am calculating the derivative at point I, this is derivative at point I plus 1, parameter at point I plus 1 minus I minus 1 divided by 2 delta x. So it means one node in the forward direction, one in the backward direction. So that's why I am calling it as central difference scheme. Okay. So likewise, if I have to calculate the second derivative using central difference scheme, del square u by del x square at point I, that comes out to be u at point I plus 1 plus u at point I minus 1 minus of 2 ui divided by delta x square. So this is the central difference approximation of second order derivative. Is this one clear? I am not deriving this, I am just giving you the idea. And because already in the first order I have given you brief idea from where this comes. Okay. So it means that if I use the finite difference method where I have divided the entire domain into large number of discrete locations and all the discrete locations are arranged in a regular and structured arrangement. Okay. So in this scenario, I can easily calculate the first order and second order derivative terms with the help of value of parameters known at different points. Is this point clear? So this way we can solve the partial differential equations and we can represent these in the form of algebraic equations, and then algebraic equations we can solve using the finite difference method. Okay. So if I have to give you one example, I can simply start with the one-dimensional conduction problem inside a rod or tube. Say you have 1D heat conduction problem, okay, and it is specified in the question that the length of the rod is L and this particular face is maintained at T1 temperature and this face is maintained at T2 temperature. You have to determine the temperature profile within this rod under the steady state conditions. Is this one clear? All are clear with this idea? So this is a solid rod, its conductivity is given as K, and let us consider A is cross-sectional area of this rod. Okay. Now it is given in the question that left face at x equal to 0 it is maintained at temperature T1 and x equal to L is maintained at temperature T2. And also let us consider it is given that T1 is greater than T2. So ultimately what will happen? The heat will transfer from one side to the other side, okay, and because of this heat transfer there will be some gradient of temperature and ultimately we need to find the temperature variation at different points along the length of the rod. Okay, so that is our question. So if this question is given to you, then from our theoretical understanding of heat transfer we know that what will be the equation for steady state one dimensional heat conduction problem. What will be equation? Inside a rod having constant thermal conductivity. Ka d square T by dx square equal to, because there is no heat generation also, so this has to be equal to 0. Is this point clear? So this is my governing equation. Now what I need to do? This governing equation I have to numerically solve and I am having only the one dimensional problem. So for one dimensional problem I need to define the one dimensional line elements. Okay. So say these are my node points where delta x is the size and we have uniform spacing delta x between all the node points. Is this one clear? Now this will be 1, 2, 3, 4, 5, 6, so on up to, if I consider that I have 10 number of node points, so then what will be my delta x? L by 9. Okay, because I have to consider the gap between the two. Okay, is this one clear? So now please tell me how I can start. How I can start if I have to apply? Yes. So what I need to do, first this equation I need to write in algebraic form. Okay, so how I can write it in algebraic form? So in a generic way, I can consider take k and a to the right hand side, and simply I will be getting that d square t by dx square is equal to 0. Now in general form, I need to estimate d square t by dx square at point I. What it will be? Divided by delta x square. Okay, so this will be my for ith node. Now I need to define boundary conditions. My first node is having temperature equal to T1, or to make it more generic, let me write it T naught, and this let me write TL. Okay, so T naught and TL. So first node is having what temperature? T naught. The node for which temperature is already known to us, I need not to solve the equation. Okay, and last node is having temperature TL. Now I need to vary the value of I from 2 to 9, because that is where temperature is not known to us. So only on these conditions I need to determine the temperature. So what I will be doing, first I will be writing for say node number 2. What I will be getting for node number 2? D square T by dx square at node number 2 will be equal to T at 3 plus 1 minus 2 equal to 0. And from here simply I will be getting equation as T1 minus 2 T2 plus T3 equal to 0. Likewise for third node I will be getting T2 minus 2 T3 plus equal to 0. Is this point clear? Likewise what I will be getting? I will be getting number of equations, and ultimately what I can do? I can segregate this in the form of Ax equal to B, where what will be X? T2, T3, so on up to T9. Whenever I am considering T2, what I will be getting? Minus 2, T3 I will be getting 1, all other will be 0, 0, and in the right hand side from equation 1 what I will be getting? Because in the left hand side I have only considered this much, so in the right hand side it has to be minus T1. Okay, then for next one, T2 is 1, T3 is minus 2, T4 is 1, and this will be 0. Is this one clear? So like this I will be getting a system of equations, and if I solve this system of equations I will be getting values of T2, T3, T4 up to T2. Is this one clear? So this is a simple representation of a simple example for which even you know the analytical solution, but I have shown you how this can be solved in a numerical manner. Okay, the only simplification was over here that we were interested in the steady state solution. So in a single step we were getting the entire solution. Okay, however, if I have to consider this solution as function of time, then how it will be propagating? Okay, so if instead of steady state heat conduction I consider transient 1D heat conduction, now what will be happening? Please tell me. I have the same problem, okay, but the physical scenario is slightly different. Physical scenario is at T equal to 0, the temperature of entire rod is T naught, but at T greater than 0, I have maintained X equal to 0 at temperature T naught and X equal to L at temperature TL such that TL can be greater or lesser, whatever you want to take. So in this scenario, let us consider TL is greater than T naught. Okay. So now what will be happening? Please tell me from your physical understanding of heat transfer. If I consider that from physical understanding of heat transfer, if I consider that this is my different x location, so this is x equal to 0, this is x equal to L, and this is TL, and this is T naught. Okay. Initially, what was the rod temperature? T naught. So this horizontal line will be applicable for T equal to 0. After that, what you have done? Say, now there is some time T1. At some time T1, what you have done? Left portion is at TL and right is at T0. So physically we will be finding that in the zone close to L, there will be sudden gradient of temperature, and in the remaining portion it will be almost 0. So this will be true for T1. What will happen when, if your boundary conditions are fixed, that T0 and TL are maintained constant, then what will happen? After some time it will be like this, then after some time it will be like this, and ultimately it will become a straight line. Okay, so it means this is T2, T3, T4, and this is some time, large time interval, after which my solution has become actual temperature gradient has become a straight line as per the imposed conditions. Is this one clear? So if you have to solve this type of problem, then what you need to do? First you tell me what will be governing equation for this? What will be it equal to? So Ka into del square T by del x square will become equal to, we are not talking about convection over here, we are talking about conduction over here. No, we are only talking about pure conduction. So in the pure conduction equation, there will be one time term which will be representing the variation of temperature in the body with the time. What is that term? Some of you are studying heat transfer in this course, so have you not studied this conduction equation? Rho Cp into rate of change of energy. So mCp delta T. mCp delta T is the amount of energy. Whenever I am dividing it with the time, then it is becoming rate of change of energy. Whenever I am writing the left hand side is written on per unit volume basis. So that's why in the right hand side also I am writing it on per unit volume basis. So mass is rho into V. If I do per unit volume basis, then V is gone. Is this one clear? Now what I will be getting? What is this rho Cp? Sorry, rho Cp by K. What is this? K by rho Cp is, or you take it on the other way. What is K by rho Cp? Thermal diffusivity, alpha. Okay, so alpha A into del square T by del x square equal to del T by. Okay. So please recall your concepts of basic heat transfer. Now, what we have? So you can see you have del square T by del x square term, which was as usual we have seen in the previous case. So del square T by del x square at point I will be equal to T at I plus 1 minus 2 Ti plus Ti minus 1 divided by delta x square. Other than this, what we have? Del T by del T. Okay. So this I can write, because I am considering on ith node, I have to calculate it on ith node. T at I. Now this solution should march with time. So once we are marching with time, I will be using time term in the superscript. Spatial index I am using in the subscript. So temporal index I will be using in the superscript. So Ti at n plus 1 minus Ti at n divided by delta T. Okay. The way in spatial direction we divide our domain into small element, in the similar way the entire time period from 0 to T final we divide into finite number of discrete time steps which are given by delta T. Is this one clear? All are clear with this point or not? Okay, so in the time direction also we have divided the time, total time period into finite number of small time steps. Is this one clear? Now, one interesting point is, over here when I am calculating this second derivative term, what I have used? Central difference scheme. When I am using this, what I have done? Why I am using forward difference scheme over here? Yes, so it means that in terms of time, it is difficult for us to go to the past. Okay, based on the present, I can move forward in the time direction. Is this one clear? So that's why for time we are using the forward difference scheme, but ultimately for space we are using the central difference scheme, which shows dependence on forward as well as the backward cell. There is a reason for using this dependence also. I will explain you further why we are using central difference scheme over here. Okay. So if I do so, then ultimately if I have to write it for ith node, what I will be getting the equation? Ti at n plus 1 minus Ti at n divided by delta T equal to divided by delta x square. Is this one clear? Now you have to understand one important point. In the left hand side, what I am using? I am using the time levels. One is time level n and other is time level n plus 1. So whenever I am using the time level in left hand side and my problem is transient nature. What is the meaning of transient nature? You can see that with the time your value of temperature at different locations is actually changing. So you have to decide, whenever you are trying to calculate the right hand side, you have to decide at what time level you are calculating this. Okay, at what time level you are using all these numbers. Okay, so there are three approaches to do this. First approach is where at present time level only we estimate all these parameters. Okay, at time level n only. In this scenario, what will be happening? Say my n is equal to 0. What it means that I am working at the starting condition, initial condition, which is T equal to 0. At this point, what was temperature of all node points? T1, T2, T3, so on up to all will be equal to T0. Okay, so all these temperatures now are known to me. what I can do, by knowing all these temperatures, delta X also I have decided, delta T also I have decided. By knowing all these temperatures, if I apply this equation for node number 2, I can calculate the value of T2 at time level n plus 1. Is this point clear? Simply from this side, all other parameters in the equation are known. I can easily calculate this. Okay. Likewise, if I go for I equal to 3, then I will be able to calculate T3 at n plus 1. Likewise, I will be getting the data for all the nodes at time level n plus 1. So once I am having data at time level n plus 1 for all points, it means at that particular time I have obtained the temperature value. After this, what I need to do? I need to further calculate for time level n plus 2. Whenever I will be calculating at n plus 2, then my, what was n plus 1? N plus 1 will be nothing but T0 plus delta T, because delta T difference you have taken. When you will be calculating for n plus 2, then your n plus 1 will be becoming the present value. Okay, and after calculating that, you will be getting at n plus 2, your time will become T0 plus 2 delta T. All are clear with this point?
The first step, it will be simply Tin plus 1 is equal to Tin.
Yes. In the first step, why?
Because
Okay, right hand side will be cancelling down. Yeah. So that will be only true for intermediate nodes when we are considering T2, T3, T all equal to T0. But whenever I will be just imposing the boundary condition in the next step, which is T1, T0 and Tn, then one boundary node will be also coming into picture whose temperature will be other than T0, and that will try to propagate its effect with the progression of the time. Is this point clear? All are clear with this point? In first step, of course, it will simply be coming out to be the same, but if I say that my boundary is imposed from first step onwards, then I can take last temperature TL equal to, the temperature of the final boundary node equal to TL, and its effect will then start propagating. Is this one clear? So all are clear with this idea? Now, whenever I have given you these simple examples, here I have only considered the conduction effect. Okay, but ultimately whenever we have to go for flow of fluid, then we have to also take into account the effect of the flow velocity. Okay, so to understand that, of course the flow equations are more complicated. As I have already told you, we have continuity equation, 3 momentum equations in each direction and 1 energy equation. But to understand the effect of flow, before going into the exact equation, we can start with one simple generic equation which is called as scalar transport equation. What is the meaning of this? Meaning is, I have a scalar quantity. How that scalar quantity is propagating in any given flow situation, if we have to understand that, for understanding that actually we can solve the scalar transport equation. Okay, so I can consider phi to be my scalar quantity, and for calculating the value of this phi, I will be having different terms. Can you tell me what are these terms? What does first term is representing? it is representing transient term or variation in value of phi with reference to time. What does second term represents? This is advective or convective quantity. What it represents? Variation in phi with the flow. Okay. Third term is diffusion term. This variation of phi inside a static fluid medium. And third quantity is called as source term. If you have to understand this, you can take a simple example to physically understand. You can consider that at the center there is a pile of wood and all these woods we are actually firing. Okay. So during the combustion of this wood, what will be happening? During the combustion of wood, heat will be released. Okay. Because of the combustion process. So what happens when heat releases? Temperature of the media increases. So what I can consider that if phi is my temperature, then I can consider once we are burning the wood, then because of that burning, whatever the fluid temperature is rising, that is my actually source term to the temperature. Okay. Now consider that in this wood fire, all of you are forming a circle and all of you are standing at equal distance from that source of wood fire. So ultimately, because all of you are forming a circle, so radius of the circle, all you will be standing at the same point, and consider that whatever the air medium is there between that fire and you, that medium is actually stationary. So ultimately what will be happening? If I consider fire to be symmetric, then all of you, whatever temperature you will be experiencing, that will be same. Is this one clear? And if you make a small circle, if you come close to the fire, then you will be experiencing more temperature. If you form a big circle, then it means you are going away from the fire, then you will be experiencing less temperature. Is this one clear? So fire is representing the source term, but whenever you are forming the circle and medium along in between the fire and you is stationary, but still you have experienced that all of you are getting almost the same value of the temperature. Moreover, when you are coming close, then temperature is increasing, and when you are going far, then temperature is decreasing. So ultimately it shows that even if the medium is stationary, stagnant, some portion of temperature is propagating from source to the surrounding air molecules. Okay. And when you formed a circle, you observed that at any direction along the circle, the value of temperature felt was same. So it means information, whatever this temperature field is propagating, in all the directions it is propagating at the same pace. Okay. So that effect is called as actually diffusion effect. Whenever your fluid medium is stationary, and in that stationary medium, if any quantity is propagating because of the transportive property of that material, that quantity is called as diffusion. For example, in this case, fire and yourself, you have air, and air is having some thermal conductivity. So because of the thermal conductivity of the air, some temperature will be moving. Okay, but this thermal conductivity is having uniform value in all the direction, and because of which it is spreading, this temperature is spreading uniformly in all the direction. So that is my diffusion term. Now what I do, along with that fire, I also place a fan. Now what does this fan is doing? It is blowing air in certain specific direction. So now one thing has happened, that flow has not remained stagnant. Now flow is having certain motion also. So what you will be experiencing, like earlier what was happening, if this was the source of fire, in all the directions heat was propagating at uniform value. So this should be circle T2, and T2 was less than T1. Now whenever you have used a fan, say this side there is fan, because of the fan what will be happening? What is happening now? The people, some of you who are facing the direction of air flow, you will be experiencing more, even if you stand inside a circle. So initial circle will be like this, then there will be next circle, then there will be next circle. So you can see, even if you are standing inside a circle, the people who are facing in the direction of the flow will be having more temperature, will be receiving more temperature in comparison to the people who are actually not standing in the direction of the flow. Okay. Now what has happened? The temperature field has started transporting because of the flow also. Diffusion is something which is the inherent property. You cannot avoid diffusion, because if medium is present, then because of the transportive, because of the thermal conductivity of the medium, heat will be propagating uniformly in all the directions. But in addition to that, the flow of air has started in a certain direction. Okay, so because of this flow of air, now the air which is passing through the fire and moving in the forward direction, that will be typically having more temperature in comparison to the air which is behind the fire and not in the direction of flow. Is this one clear? So now what has happened? The variation in the phi has started because of the predominant direction of the flow. So what is the contribution of the flow on changing the value of temperature? That is coming in this advective and connective. Is this one clear? Now along with this, you also consider that initially you are burning fuel or you are producing fire at certain rate. Now you have immediately increased the rate of the combustion process. So ultimately what will be happening? At some time you are burning fuel at certain rate, at other time you are burning fuel at higher rate, at some third time you are burning fuel at some more higher rate. So ultimately when you are increasing the rate of combustion process, then upon increasing the rate of combustion process, your temperature value will also be affected at the source itself. So the variation in temperature value with time is accounted for in the extra. Is this one clear? So this is how this mathematical equation you can make its connection with the theoretical mathematical with the physical scenario. Okay, you can also take a simple example. If you consider a water pool and this water is stationary, at the center you have placed a heater, what will be happening? Heat will start propagating into the water and propagation of this heat will be in the form of concentric circles. Okay, but if you allow water to flow in this direction, then what will happen? The water behind the heater will be cold and after the heater it will be hot. Okay, so it means that the diffusion is having characteristics that information should propagate uniformly in all the directions. But whenever you are introducing the flow, then flow tries to channelize the transport of property in a certain direction. And the competition between the flow and the diffusion, which rate is more controlling. If you have flow but flow is happening at very low rate, then your there will be deviation from the circle, but the deviation will be very less. However, if flow is predominant, then the temperature profile will be more elliptic. Is this point clear? All are understanding this point? So depending upon the dominance of convection or diffusion, we will be having actually variation of particular phenomenon. All are understanding this point? And at the same point of time, whenever heater is maintained at constant rate, then ultimately at some point of time we will be getting a steady profile which will not change with time. But ultimately, if heater is having some variation in the amount of heat which it is supplying, then ultimately we have to account for temporal term also into our analysis. Is this one clear? So, in order to understand, whenever we will be having fluid flow, there will be four important contributions. One will be because of the transient nature of the flow, which is the time term. Other contribution which will be existing always, which you cannot avoid, that is the diffusion, because diffusion is something which is inherent property of the material. If you have some hot medium at the center and in the surrounding you have fluid medium, the thermal conductivity is inherent property of the fluid medium. If fluid is present inside a hot environment, it will be transporting the heat unless or until you make certain provisions to isolate that fluid from the hot medium with the help of insulation also. Okay, so that is inherent property. Diffusion will be always present. Then other than that, the effect of diffusion can be countered or channelized in a particular direction if you induce the flow. So flow is accounted for in the mathematical analysis with the help of advective term. And other thing can be a source term, which is actually can be leading to generation or decrease in rate of a particular quantity for which we are trying to study the transport. Okay, you can also understand over here from the equation itself, in the diffusion term we have which quantity? This particular gamma is actually property which is called as diffusion coefficient. So diffusion coefficient for heat transfer is thermal conductivity. Okay, is this one clear? Okay, so if you derive this equation from the first principle, then we will be able to understand that. Let us not consider that at the moment. Okay, what you can do, you can simply refer to your energy equation and try to compare the energy equation with this equation. You will be finding this equation. Okay, and even in advective term, what I have mentioned that it is coming because of the flow. So you can see one velocity term is there. So this velocity term is actually representing the motion because of the flow. Now, as I told you in this previous equation, for del square T by del x square, we are using the which scheme? Central difference scheme. Can you tell me first, alpha A del square T by del x square, this is which term? Diffusive term, advective term, or source or temporal? This is diffusive term, it is involving thermal conductivity, and you can also see it is involving second derivative. And here in the diffusive term, if I consider gamma to be constant, then del and del will be becoming a Laplacian derivative, which is a second order. So it means that this term is nothing but diffusive. Now what is the characteristic of diffusion? Just now we have seen. The characteristic of diffusion is it propagates uniformly in all the directions. So as diffusion is propagating uniformly in all the directions, whenever we will be numerically calculating the derivative for diffusion term, we should also take into account the variation of that numerical scheme in all the directions. We should not take that variation in certain specific direction. because physical nature of diffusion is it propagate uniformly in all the directions. So that's why whenever I am calculating the when I am calculating the derivative term, I am using the central difference scheme, which for a particular node represents the dependence on forward node as well as on the backward node. Is this one clear? Because diffusion term propagates uniformly in all the directions, so that's why for resolving numerically the diffusion term, we have to consider dependence on all the directions. Is this one clear? Okay, so probably I think I will take one more lecture to explain basics of CFD, and then we will switch for CFD of multi-phase fluids. So I'll stop for today.